Here's a periodic trends question that asks us to consider electron affinity. Like most of the other trends, we see an increase in going from lower left to upper right. Now in this case, what we mean by an increase is more exothermic values for the electron affinity. It's always an energy releasing event when you bring a new electron close to a positively charged nucleus. And the question is just how much energy is released when that happens. So in part A, they want us to rank nitrogen, oxygen, and fluorine. And they're all in the same period, so just going from left to right, and they're asking from least exothermic to most, so that would be from anywhere in the lower left to anywhere towards the upper right. So nitrogen followed by oxygen followed by fluorine. Problem B is a really interesting one. Here we've got aluminum, silicon, and phosphorus, and they're right next to each other on the periodic table. Groups 13, 14, and 15. You might think that it goes in that order: aluminum followed by silicon followed by phosphorus. But there's an exception. The best way to understand the exception is to draw an orbital diagram. So let's do that for both silicon and phosphorus. So orbital diagrams are the series of boxes that we fill with arrows indicating electrons. So first, silicon with 14 electrons in a neutral atom. The nuclear charge is 14. So if we follow Aufbau principle, Hund's rule, and the Pauli exclusion principle, we come up with an orbital diagram that looks like this. The electron configuration for neutral silicon ends with 3p2. How about for phosphorus? Phosphorus has a nuclear charge of 15, so if it's neutral, we'll have 15 electrons, just one more than we had in silicon. Neutral phosphorus has an electron configuration that ends with 3p3. Now, if you're adding one more electron, where would that next electron go? Well, in the case of silicon, it would go in the third orbital in the 3p sublevel, resulting in a half-filled sublevel. There's an extra energetic favorability in achieving a half-filled sublevel. In the case of phosphorus, it already, when neutral, has a half-filled sublevel. Adding one more electron doesn't do anything especially energetically favorable, other than it generally is favorable to add one more electron. Now the general trend goes from left to right within a period, and the reason for that is you've got more protons as you go from left to right. If you have more protons, you have more of an ability to attract extra electrons, a greater magnitude of positive charge in the nucleus to attract any extra electron brought near it. So in this case, we have an exception to the general trend. You would think aluminum followed by silicon followed by phosphorus, but because of the addition of one electron resulting in a newly half-filled 3p sublevel, the trend is aluminum followed by phosphorus followed by silicon. We see that trend in both the 2p sublevel, so if you compared carbon to nitrogen, you would see that same exception. We see it with silicon and phosphorus. But by the time you get to the 4p sublevel, that exception goes away. And down below that, there is no further exception. You just follow the general trend. And the reason for that is, as you go down the periodic table, the valence electrons are in sublevels that are held farther from the nucleus. And if they're held farther from the nucleus, then any of these effects are seen in diminished form.